A binary search tree has such a great property. For any given node, the values in the left subtree of that node will always have values lesser than the given node, whereas the values in the right subtree will always have values greater than the given node's value. In this video, we're going to talk about the problem in which we are given a binary tree and we have to validate if it's a binary search tree or not. Now, a lot of people come up with solution keeping the condition in mind that, for a given node, we'll check if the left values is less than the node value and the right value is greater than the node value. But this is a very local solution and we'll see why. And then we're going to discuss the correct solution as well. So without wasting any further time, let's get started. All right, so let's take a look at the sample binary search trees and let's devise our algorithm, right? So I'm having two binary search trees over here. And if I see the first one, let me just quickly change the ink as well. Yeah, sorry about that. Yeah, so now I have this, let's validate if this is a binary search tree or not, right? So I have 3 nodes in my binary search tree. And what's the property of binary tree? That for any given node, its subtrees on the left and subtrees on the right will have a property. What property? The value of the node on the left will always be less than the value of the node that we are considering, and the value of the right child will always be greater than the value of the node that we are considering. So in this case, we have 2. The value of 3 greater than 2, right? And 1 less than 2. This validates BST. So this is a BST. So this is a BST, right? And if you come to this one, for this node, we start checking from the top, right? So we'll say, okay, for 5, we check if the left subtree is less than 5 or not. So yeah, it's less than 5, left node value, right? And the right should be greater than, but is 4 greater than 5? No, right? So this is not a BST. So with this, we can devise a logic, we can have something like, let's make this, if we had another BST as well, in which we had, say, suppose 5, 1, 8, 6, 9, something like this, right? So what we'll do is we'll first check this root value and we'll check if for this it satisfied the condition between left and right, right? So it's satisfied. Then we go down to the left child as well as the right child. So in the left child, we'll check if this has any children or not. So this does not have any children. So we just return true from here. I will write code for this, no problem. Don't worry. And for this, we'll check if the condition is true. So for 8, the left child is 6 is less than 8 and 8 is greater than 9. So both the conditions are true. I mean, sorry. 9 is greater than 8, right? So both the conditions are true. The value in the right node is greater than the root value for this subtree, and the value on the left is less than the node value, the root value for this subtree. So we say that this is a binary search tree. This is correct, right? So based on this, we'll devise an algorithm. Now for the who wants to know that this is correct or not, this is not the correct solution, but I'm gonna still code it and find out a test case where this fails. This looks correct, but this has a big shortcoming, so we'll discuss that. So I'm back again on lead code solving this problem so that we have a lot of test cases rather than coming up with our own. And we're going to solve it using the algorithm that we devised in the last section, and let's see if we are able to find the test case on which this fails. I'm going to write the code. So, for this given case, we have 2, 1, 3. Now, according to the algorithm that we have, 2 is greater than 1 and 2 is less than 3. So this is a BST. Then we go into the left and right subtrees. So for 1, there is no children. So what do we do? There are no children. So what do? We return true already because this is a binary search tree. There's no reason to say it's not a binary search tree based on the fact that there are no children, right? So we return true. So, and if there is nothing, then also it's a binary search tree, because with 1, I'm going to say, I'm not going to check if it has left subtree, right subtree or not. I'm just going to go away. So, I'll say if root is equal to null, then return true. Now, if we have left subtree and root.left.val is less than root.val, then we say return, rather make it a little easier, we'll say return false. And if we have root.right, we have right child, and then we check root right val. So checking the value of the right subtree, if it's right node of the given current node, if it's less than the root's value, then it's definitely wrong, so we'll return false. Then return is, then we just do recursion in the left and right subtree. So we'll say root dot left and root dot right else is valid BST. All right, so seems correct. Let's try it out. All right, so we get a semicolon. All right, so do we have a bracket missing or something? Yes. Let's run code. Root right val is less than, oops. All right. So it's accepted. Let's submit it and try it out. So it fails on this case 1 1, so which means there is a node 1 and has left subtree zones. Okay, so they want us to allow same values as well, so greater than equal to and less than equal to. And now let's try. We get wrong answer on this on this case. Let's see why. Okay, okay, all right. Let's take a look at the test case. 5 4 6 null null 3 7. So we have a tree something like 5 4 6 null null 3 7. So 5 4 6 null null means there are no left and right child for this, and then we have 3, then we have 7. Our code gave the answer as true but expected was false. Take a moment and find out what's wrong. You are free to pause the video. For those who just want to enjoy and continue, let's see. So the property is 5 4 6, correct for this node. We go down, here we return true, right? Let's just change the color to red. All right, and for same thing for this node, 6 is greater than 3 and 6 is less than 7. So according to our algorithm, this is BST, right? But the value in the right subtree I see corresponding to this node in the right subtree, there's a value less than this node. 3 is less than 5. That's the big shortcoming of this algorithm. Binary search tree's property is that globally the values in the left subtree are always less than the values present in the right subtree and the node and the root. For example, if you take a look, if you take a closer look to the description as well, the left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only right subtree. So everything in the right subtree, right? So that's why this code fails. Now let's improve our algorithm, existing algorithm, and solve it correctly. The algorithm is not the only wrong thing here. Another wrong thing is watching this video without subscribing to the channel. So if you see that red subscribe button, make sure you hit it. And now let's fix the algorithm since the other problem is fixed. All right, so now to fix the solution, we need to take care about whenever we go down, one thing to make sure is each node will have a maximum and minimum value. Let's see why. So if I come to 4 in the left subtree now any value, suppose if there would be another value like 1 or 2 as well, not 2 but something like 4.5, just for consideration. The main thing is that these values in this subtree now cannot be greater than 5. They should always be less than 5, right? And the values in this subtree should always be greater than 5, right? And now when you come there, the values here should always be greater than 6, right? So this idea of keeping the bounds and passing it down to each level of the tree is the key to fixing our problem, right? So let's see how. Let's see it in the implementation. I'm going to teach you how we can pass these bounds as well, right? So let's take a look at. So now let's take a look at the code that we wrote earlier and let's fix it. So the idea that we discussed right now was, the thing is, we have to pass the value of bounds to the to the lower subtrees as well. Now the important thing to consider is at every level now as we discussed, we'll have a min value and we'll have a max value. But the point to note is, in the left subtree, I only care about a maximum value, right? All the nodes in my left subtree should be smaller than a given value. And in the right subtree, I only care about the min value. What it means is all the values in my right subtree should have a value greater than this minimum value. If this condition is wrong, so what I'm saying is root val should either be, should be greater than, should be less than maximum, and let me just erase this and write this in a better way so that it's easier to understand. So what I'm saying is the left subtree root dot val should always be less than a maximum. So root dot val should always be less than a maximum. In the right subtree, root dot val should always be greater than the minimum. If these conditions are false, then we can say that the tree is not a BST, right? So let's change our code to reflect this. So I'm going to say our function now accepts int min and int max, which I'm going to assign to large values, int max, right? And now this thing, do we really need to care about left or right? As the two conditions that we have is the value should be less than maximum or the value should be greater than minimum. So we're going to write the opposite of them. So I'm going to say if root dot val is greater than maximum or root dot val is less than minimum, then return false. So what this tells us is sometimes it's not always good to check on the condition which makes sense. Always try to take a look in recursion problems specifically. Sometimes the negation case is more easier to handle and to code. So let's submit this and see if this works. We just made a mistake in. Okay, I'm going to make this full screen. Got a wrong answer. Okay, obviously I'm going to get a wrong answer because I did not pass my minimum and maximum also here. In max, min, max, and let's submit now. We again get a problem 51436. Okay, int min. All right. So the error again is, so what we missed is, so for now when you come down you have to change the bounds as well, right? So we change the bounds. How do we change the bounds? For the left subtree, if I again show you guys, for the left subtree the maximum value possible now is the root value, right? 5, and as soon as we go down in the left subtree the maximum value decreases. So on in the right subtree the maximum value the minimum value always increases. So that's we're going to reflect in our code, and we're going to do it like so. For root dot left, the minimum value we don't care, but the maximum value should always be this corresponding root's value. And similarly for the right subtree, I'm going to just write it in the second line. For the right subtree, the minimum value we care about is root dot val, and the maximum value is we don't care about it. It can be as high as possible. So let's submit and run this now, and let's see. We get it wrong, and the condition is that all the keys are unique, right? So if root dot val is greater than equal to max, it should not be equal also, right? So less than equal to, it should not even be equal. Now let's run it. So the people at LeetCode are really very, very tricky. So one last hurdle, I think should be the last hurdle to pass, is they do not want us to use these integer ranges. So I'm going to change it to long, make this as long min, and again do the same thing, make this as long max, and also change this type as long. Now let's submit it. Finally, the problem is accepted. So I really like this problem because a lot of people find the first algorithm very obvious and very intuitive, but actually it's wrong. And now you know why, and I think you'll remember after this. So So well, with that, we end the discussion of this problem. I hope you enjoyed it and I hope you remember this concept and do not forget it. A lot of problems can be based in future on this concept as well. So always remember the passing the bounds min and max to the lower levels of the tree as well to check if it's a BST or not. So if you guys enjoyed this video, give this video a thumbs up, and if you haven't subscribed to my channel already, then please subscribe to the channel. And until next video, take care. Bye bye.